We often hear that the path to fault-tolerant quantum computing will require error correction. How will this technique work? We cover this and other scaling technologies in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CTO of Quantum Machines, Yonatan Cohen. Welcome to the show.
Hi, thank you for having me. I'm very excited to be here.
Awesome. Yeah, let's dive in. There's a lot to cover here. But first, I just wanted everyone to get a sense of who you are and how you found your way to quantum computing. I know you have sort of the traditional route, right? A PhD in physics, of course. That's a good traditional start. So I guess first question would be like, were you interested in quantum computing when you were doing that? Or just did you find your way to it like after?
Yeah, I was interested in quantum computing. Indeed, I did kind of the standard way, at least today in the industry, which is to do a PhD in quantum physics. But I actually started to become interested in quantum computing in my bachelor degree, which I actually did in the United States, in Seattle, University of Washington. I had a very good teacher I took this course, Quantum Computing 101, and that kind of blew my mind. I thought it's a much better way to actually study quantum mechanics than to, start with atoms and electrons. Just start with these abstract things, which are these qubits, and it really blew my mind. And that's where I started thinking about quantum computing. And I was always kind of interested in entrepreneurship, but it was not until the end of my PhD that I found my partners and started a company in the field. Yeah,
that's great. So you, it's once again we're hearing about this idea of a professor who changed someone's view. So I think that's terrific, And I hope to all the teachers out there they hear that. You can have a really big impact at a key moment in someone's development.
Huge impact.
Yeah.
I mean, this guy, his name is Boris Blinov. He's just amazing teacher and amazing person, and then that's what impacts you, right?
Yeah, absolutely. And then it looks like not too much after you got your PhD, it was onto quantum machines, right? So what was the first gem of an idea you had then? What was the passion for what you wanted to bring to the industry right out of the gate like that?
So taking maybe a step back.
Mm-hmm.
So during my PhD, I was working on looking for what's called topological quantum states, which have a potential for them to allow us to make error qubits that are protected from errors. So that's kind of where my research was. But at the same time, me and my friend from the PhD back then, Itamar Sivan, were also thinking, oh wow, it'd be awesome to start a company one day. And so in parallel to our PhD, we started an entrepreneurship program at the Weizmann Institute in Israel, which is where we did our PhDs. This was the first time that there was such a program at the Institute, so we got a lot of attention from community, from investors and so on. And then when we kind of graduated and thought what do we want to do, it was clear that we would start a company. We actually didn't start right away from quantum computing. We had lots of stupid ideas, machine learning, all that stuff that everybody's attracted to. And at some point, we sort of saw that investments are starting to rise in quantum computing. It was 2018. And that's where we were kind of, okay, something's happened. Quantum, maybe we should look at that because that's really the only thing that we know. But what was very important for us, the one lesson we kind of kept from the entrepreneurship program that we ran ourselves was we wanted to be in a place sort of in the stack, in the quantum computing stack, where there is a current need for products, not future need. of course, the need in the future, the market will grow significantly once quantum computing becomes, super impactful on industries, and then the requirements for our products are going to grow. But even today, there's a large enough market for to grow and to become a successful company. So that was important for us to have a market lead already today. And the other thing that led to what we do at Quantum Machine was that we knew our third co-founder, who was just came back a year before from his postdoc at Yale University in Professor Rob Shurkov's group, which is one of the leading superconducting qubits group in the world today. And during his postdoc there, he really developed very, very significant technology there that allowed him to perform the first experiment actually of quantum error correction done on superconducting qubits. So that was a big milestone. So of course, when we were like, okay, there's investments going to quantum computing, we should call Nissim. So we called Nissim, and then the three of us kind of started thinking together, and we realized that there is a place in the stack where there is current need, and that there is also a current, so there's a current bottleneck and very significant technology to be developed that's going to be important, going forward.
Okay.
And that is what's called the control system of the quantum computer.
Okay, so let's dive into some of these points in order. So first of all, you were interested in topological quantum computing. And so you must have been excited by Microsoft's Majorana Fermion topological gap paper last year.
Look, to be honest, this was, what we did in our research is not exactly what we're doing in the company, but definitely looking at the physics of topological quantum system is one of the most exciting physics that's happening today in the world, I believe. And seeing such great progress done with this system is definitely exciting. So, I do think that there is still a long way to go until we can base out computers.
It's going to be a while before we have a Majorana qubit. I think it's going to be a little bit. And of course, that would be virtually error-free, so that'd be great. But because we don't have that, the more logical approach right now is to also be working on error correction. So I definitely wanted to spend a few minutes digging into that. If you want to maybe take a step back and explain some common error correction methods and sort of what your company is working on, so that way our listeners can get a sense of what that really means. Because I'm sure they conceptually have an idea, but just to dig in a little bit.
Sure. So first of all, why to do quantum error correction? So so we have already quantum computers, and they even work, at least to some extent, they work. But we are in what we call the NISQ era, or noisy intermediate scale quantum devices era, where our current quantum computers, they have a very high error weight. So if I run the same experiment twice or same circuit on my quantum computer, I can get different results, not just because of quantum statistics, also because of errors. And there are certain algorithms which might be useful running on these NISQ type quantum computers. But they are heuristics, so we don't know whether they will work or not. We just need to try that and see. Hopefully, they would give us some advantage, but we don't know that. And also, we do know about quantum algorithms that will give us significant computational advantage if we could run a quantum computation that doesn't have any errors. So that's the reason why that's called a fault-tolerant quantum computer. A quantum computer where I could run my entire circuit without having any errors. Now, the mainstream way to get to a fault-tolerant quantum computer is to perform quantum error correction, which is a way to actively correct for errors. So it's, you could just say, let's just build a qubit that doesn't have any errors, right? The topological qubit can just be a qubit that's super isolated from its environment. That's one way. But today, the current error weights are too high. And so the way people believe that we will be able to lower the error weight is not just by lowering the physical error weights, but by taking many physical qubits and encoding with those many physical qubits a single logical qubit. And this logical qubit, by performing certain control protocols on it, meaning that we measure some of the qubits, and by taking these measurements in real time, we can calculate what were the errors, what were the physical errors, and even correct those errors. This is called quantum error correction. Then we can make our logical qubit have a much lower error weights than the physical qubits.
That's a great basic.
And this error correction. Yeah. And by the way, Google just a week ago published new results that are very important, because for the first time in superconducting qubits, they show that when you grow the number of qubits, so until now, many people have tried to do quantum error correction, and you can see some building blocks, right? But the key here is really that you want that as you add more qubits, more physical qubits to your logical qubits, the error weights go down. Until now, it was the opposite. And now it's starting to become going the right direction.
Because if you cram too many qubits in one space, all of a sudden you're introducing new noise, and that becomes its own issue. Yeah.
Exactly.
So we need to find that optimum size. Yeah, I was going to ask you about that Google thing too.
Okay.
So if you want to explain for our listeners what's significant about the Google achievement and how you view the number of logical qubits by technology. Do you have like an overview of what you're seeing in the industry? What would be good guesses at how many physical translate to logical by, let's say, by type, like transmon, trapped ion, and any kind of views like that?
It's a very good question. So first of all, the significance of the Google experiment, I think that, it's very significant to show that as you scale up your code, what's called the code distance, which basically means how many physical qubits are used to encode my logical qubit, I can lower the error weights and not the opposite. Okay? And that means that I could continue to scale. In theory, I could continue to add more and more physical qubits and lower my error weights to as much as I want. Yeah. And that is how I build a fault-tolerant quantum computer. So, of course, this is in theory, and the fact that I went from code distance 3 to 5 and the error rate goes down doesn't mean that it will work when I go from 5 to 7 or from 7 to 700, but it's a very significant first step, very important, actually critical in order to continue to believe in this route. So that was that. On the other end, I think the road is still very long. In superconducting qubits, people talk about, with current error weights, about 1,000 physical qubits to make a logical qubit.
The terrifying IBM number.
Exactly. Yeah. And that is still quite far. You need and that's for a single logical qubit. Then you need any logical qubits and performing gates. The good thing for quantum machines, by the way, is that means you need a very large control system to control all these qubits. And in fact, one of the key aspects that you need to perform quantum error correction effectively is what's called real-time feedback. That means that I could measure qubits while the algorithm is running, when my circuit is running. I measure a qubit. I could do classical calculations on these measurements. I can measure a bunch of qubits, and I could, based on the results, do some classical decision-making in my classical hardware. That's the control system. And even respond in real time, say, okay, if all of these physical qubits were in this state, maybe I should operate on my logical qubit this way or that way, and that in this way I could correct the errors. So this specific capability that's called real-time feedback of the control system is one of the key advantages that we offer in a control system at Quantum Machine.
Okay, so your control system doesn't just do a cookie cutter approach. It doesn't just say, oh, I have 10 qubits, I'm going to try and turn them into one logical one exactly the same way every time. It actually looks at what's going on in a particular environment and makes adjustments. Is that correct? To try and to get closer? Yes,
makes measurements. Exactly. The user could make measurements of subsets of qubits, and based on the subset of qubits, realize what is the state of, that's partially what is the state of some of the other qubits, and based on that, make decisions in real time on what gates do I apply to certain qubits to fix my errors. So
Okay.
And it's actually very interesting because we started from topological qubits. And I think one of the very interesting areas that are being explored these days is, can we make a topological state from regular qubits? Okay. Because regular qubits could simulate any other state, right?
Mm-hmm.
So I could use them to simulate a topological qubit, or to actually create a topological qubit. And then this topological qubit is protected. So in fact, taking a bunch of physical qubits and making a topological qubit out of them is a form of error correction by itself.
Yeah.
And that area of research is now very trendy. And this one also requires a lot of real-time measurements and feedback from the control system.
Yeah, that'll really hurt some people's heads quickly. They're familiar with the idea of taking a classical computer to simulate a qubit. Now you're simulating a different type of qubit with a qubit that doesn't meet that criteria.
That's true.
Yeah, that gets pretty trippy, I suppose. So are you actively looking at that right now also at your company as something to offer? And that'll get us to the next question too, because I also want to ask like who your typical customers would be for this control platform.
So I'll start with the second question actually, because yes, our customers are everyone who was developing quantum computers. Mm-hmm. We're selling a component of the computer. Okay, so if you're for example, if you are developing your quantum processor, you need a control system. Or if you're developing a full stack quantum computer, you need a control system. That's going back to the beginning. We wanted to be in a place where people who are working in this field today, they need control systems. So whether they buy it from us, whether they make it themselves, or whether they buy from competitors, it needs to be done. And so we are working with many of the leading players, startups, big companies, academic groups that are developing these qubits. We work all kinds of qubit types, so put like qubits, spin qubits, trapped ions, neutral atoms, and with many of our customers, we're also exploring such ideas as error correction, for example, demonstrating error correction protocols and HST and experiments.
Mm-hmm. Are you then seeing all the different types of error correction play out on your platform? Do you have to like modify? And the name of this particular thing, that's the quantum orchestration platform, right?
Right.
Yeah.
Right.
So are you then able to see, are you getting feedback from customers about the different types of error correction they're working on, or does that kind of like stay with them at that point?
Yes. It really depends on the customer. Certain customers are very, very collaborative. Certain customers are less. It really depends on what they do and what's kind of important. But yes, we do have a lot of visibility to what's happening today in the field, the difference between these different kinds of qubits, what types of error correction protocols people are trying to run, and what are the different requirements, because they can vary significantly. So, in superconducting qubits, for instance, this is the most demanding requirements from a control system if you want to run quantum error correction, because everything happens very fast. So you need to do this measurements and processing and feedback dimension. You need to do it insanely fast. While, for example, in trapped ions, they live much longer, so you have much more time to breathe, measure the qubits, think what you want to do, and then perform in the qubits. So we do see significant differences, and then significant differences in the requirements from the control system.
Now, I believe one of the paths to scalability is to identify the optimal number of qubits for any technology, and then just build a lot of those modules and then interconnect. Do you see your hardware and software sort of living in the interconnect space as well down the road? Are you working towards?
Yeah, definitely. I think that's one of the advantages of our system, that it's very versatile and very programmable, and that's why we managed to work with all these different qubit types, and that's why you can also combine qubit types. Some of our customers do that. in many cases, it's actually quantum networking that people are combining different types of qubits because you have the photons and you have the spin qubits and trying to move information from here to here. So photons are very good to move information from one place to another, while the spin qubit maybe is very good to preserve information. So there we see it, and people are actually using our systems very successfully to kind of combine different types of qubits to build.
Oh, that's pretty exciting. And we're seeing a lot in that. Like IBM's System 2 is a great example. They're claiming that with that new infrastructure, they'll be able to support something like 16,000 qubits in one giant array, but they're not really telling us what that interconnect is. So do you see your type of approach being used in something like that, where like multiple machines are already going to be connected?
Yeah, and I think what's going to be important also in these types of, when you start connecting different quantum chips where, you could relatively easily create entanglements locally, but it's harder to then spread the entanglement around, to a neighboring chip. There, I think, in having this real-time classical logic, classical processing and feedback is actually going to be even more important, because it can help you basically lower the overhead, the quantum overhead, by taking certain measurements and then responding on other qubits based on the measurements that you took with your control system. So it's kind of like, how much can I offload from my quantum processor to my classical compute system, which is this control system? And that becomes more and more important as, we scale up and as we get these weak links between different islands of qubits.
So how would you describe your company's role in things like hybrid, and this idea of using classical and quantum together? Is it just in that control layer that you just mentioned, or are there other areas where you actually facilitate more major parts of a computation to be on a classical machine and then hand it off?
It's a great question. So there are two kind of pillars to this. First is the control system itself. We were in fact the first to really embed general classical processing units into the control system in such a way that you can really combine quantum operations and classical operations in the same code, which is our programming language, Qubit. So Qubit really was the first to allow you to do general and classical processing. You can define variables X, Y, Z and say Z equals X plus Y, or X squared minus Y, or X divided by Y, anything that you want to do with classical processing, like in any other programming language. But the same operations, the same commands, classical processing commands, can be embedded now in the quantum control sequence. So with the gates, actually the pulses that we play to the qubits, so I shape the pulses and I can shape it based on this classical processing and all. It's very, very low level stuff in quantum computing, but that now mixes quantum and classical processing together. Okay, that's kind of control level. And that's critical again for quantum error correction, quantum error mitigation, calibrations that you want to do today. Even before we fix the errors with quantum error correction, we have huge drifts in the systems. The parameters of the system drift. Just by doing measurements and real-time feedback, we can correct those drifts. So that's kind of hybrid already on that very low level of the controller. But then, of course, you want to also get out of the controller because there's a limit to how much compute power you can put so close to the qubits. And you want to, and so it's very important to start building the right integration between the quantum computer to the general, classical compute systems that we have, whether it's cloud or high-performance computers. And that's something that we are now with Quantum Machines putting a lot of emphasis on. We already have some few projects where we are integrating quantum computers into more scalable compute hardware. Specifically in Israel, we're building the Israeli Quantum Computing Center, where we're going to have a small HPC, but nevertheless a high-performance computer that's
they're cheap,
tightly integrated. Yes, definitely. I mean, the more important for us is less how much compute power we put there to begin with, but this tight integration, the fact that we can really integrate the quantum computer to become another resources in an integrated classical and quantum system, and you can run these hybrid algorithms very efficiently on this system.
And do you feel that an HPC needs to be physically located very close to a quantum computer? Do you think that latencies and things come into play?
That's a very good question. So it really depends on what is the application that you're trying to run. So if, for example, you're trying to perform the quantum error correction, and you want to use the HPC for doing decoding of the errors, then you need very low latency, and you need to be very close to the qubits.
Mm-hmm.
In some of the other hybrid applications, like variational algorithms, like VQE and QAOA, you might be able to get away with having, not such close physical connection to begin with. But then sometimes if you're trying to do certain optimizations, for example, as a part of this hybrid loop where you run classical compute, quantum compute, but then all of a sudden you have this very heavy classical compute that you want to run inside the loop for doing some optimizations, then you might again want to lower the latency. But what's most importantly in those type of applications is maybe less to begin with that we're physically close, but more that we can schedule the resources of the HPC and the quantum computer in a unified way.
Mm-hmm.
Okay, because typically what you do is, you run the classical processing, then maybe someone else is taking the quantum computer, and then you need to wait for the quantum computer to be ready. Then you run something in the quantum computer, but then your classical computer is waiting because maybe someone else is using it. So being able to co-schedule the resources so that I get, like I do in HPC, I ask for a few CPUs and a few GPUs, and I run my entire application on these resources that I scheduled for myself. That is something that we are working on hard at Quantum.
So the current model for logistics purposes is that the big cloud providers, Azure Quantum, Bracket, AWS, they typically have the quantum computers elsewhere. They reach out to them. Yes. So for certain applications in the future, it might benefit them to have one of these boxes sitting inside their cloud stack somewhere physically, so that way they can do some of these more optimized runs, right?
Yes. I think at the end, people will want to set up, quantum computers in their physical data centers. It's not just for performance, but, it's for a lot of reasons, but performance is definitely one of them. At the end of the day, that's going to be important, yes.
Okay, and going back to Qua for a second, and for those listening, it's capital Q, capital U, capital A. That programming language is really about the pulse level control. It's not about building a whole circuit and then sending it, right? It's not some new interface for an end user to send a program, let's say.
Right. It's a very it's about pulse level control, and it's about this integration of classical and quantum processing in the same code. When we say pulse level, we mean that we don't just say, operate apply this gate to this qubit, but we really say play this pulse shape to this channel of the control system that goes to this qubit, and then play another pulse. And we also can control the timing. When are we playing? Because in quantum computing, because of the error rate that we have, the timing of these operations can become important. And now, coupled to that, the classical processing. So the fact that I could say, play this pulse, but change its shape according to some classical calculation that I performed. Okay, maybe on the measurement results. So maybe change the shape of the pulse based on some measurements that I did on the qubits just 200 nanoseconds before. Because remember, I can control timing. So I could really do all these super low level things. And today, you can say in some sense, unfortunately, but this makes it more interesting, it's really critical to optimize on that level in order to optimize the performance of quantum computers and to push forward towards scaling up quantum computers.
Yeah, so do you anticipate in the future having some kind of API hooks or something that let coders talk to Qua and say, I need a little more in this area, I need the qubits that are optimized for this, operation? Anything like that, like a little more interplay?
Yeah, I think that would be like, we already have integrations with higher level programming languages, for instance, OpenCasm 3. We've done a lot of work to integrate with OpenCasm 3 because we believe these standards are now becoming very important, and they're actually going in the direction that we've pushed for now 4 or 5 years, that to integrate classical processing with the quantum circuit. So OpenCasm 3 has done a lot of these things. So in some sense, except for the fact that it's more gate level, even though it does allow us for some pulse level, it starts to resemble Quine in many aspects. And it allows you to integrate classical processing into your code, into your quantum code. And that's why we're integrating with those higher level languages that also are becoming now standards to even higher level frameworks, such as Qiskit and even higher level classic companies like Classic and others. Once you've integrated with OpenCasm, you can now enjoy the power of the ecosystem.
That's great. Yeah, I wanted listeners to get a sense of how they might actually be touching this and not knowing it. Yeah, it could already be.
Exactly. So you might program something high level and you don't know, but under the hood, it's running QAP and quantum orchestration.
Yeah, I always say it's a full stack, and any performance you can get on any level of that stack greatly impacts performance. So I guess one last question to kind of bring this home. If you could just put your futurist hat on for a moment and give me your sense of when you think error correction will start actually showing up in the industry. Maybe if you think with one particular type of processor, that's fine. But just like a sense of the timeline when people might start seeing this be advertised and showing up. Like you log into one of the experiences and say, oh no, right now you're getting 16 error corrected logical qubits. Like when people might start seeing that kind of thing.
Wow, I think, okay, so maybe I'm not the right person to ask because I'm not the most optimistic one when it comes to predicting. I would assume that playing around with, several error-corrected qubits, that is something that we might see by the end of a decade. I think that's realistic. But really having a full fault-tolerant quantum computer that can run, the most grandiose applications, I think that's going to take even longer. In the meantime, however, I am optimistic that there is a lot of value we can extract from some of these NIST computers, hopefully, and so that we continue to push the field forward. Yes. Yeah.
For all we know, we might just get better qubits before we get better error correction.
Yes, that's true. And I think it's also it's a gradual thing. So by the way, in some sense, even when you just take a current quantum computer and use it to simulate another quantum system, which is starting to happen now, for purposes that previously physicists would use their university cluster to do that, right? Another, you have an HPC in your university and use it to simulate your quantum system. So, okay, it's not the application that we dream of that, would change the world, but it does cost a lot of money to run your quantum simulation on your university HPC cluster. And if you can do it with a quantum computer for cheaper, for less resources, essentially, then we've already shown some value. So I think that's going to be the very first value we see. And from there, it's going to kind of gradually progress. So
yeah, that's a great refreshing approach. It's cheaper and I guess better for the environment too. If you can run it on very, very low power comparatively for the amount of time it runs, a millisecond or whatever.
Exactly.
Yeah, that's terrific. Thank you so much. I really appreciate your insights and explaining some of these core concepts to our listeners and giving them a sense of what goes down that stack. I really appreciate it.
Thank you so much for having me. Happy to be here.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. Quantum Machines works on control systems for quantum computers. Their quantum orchestration platform can control a hybrid of classical and quantum processors to run algorithms. It should scale to over 1,000 qubits. They also developed a program called QA, spelled QUA, which is a cross-platform software development kit that handles classical variables and operations and passes them to classical and quantum systems. On the quantum side, Qua allows for pulse-level type programming that supports trapped ion, topological, superconducting, and other types of QPUs. The company is also working on error correction. As the name implies, noise is present in the noisy intermediate scale quantum, or NISQ, era. Error correction will be required to get to a fault-tolerant quantum computer that can run deep circuits without introducing errors from compounded noise affecting each qubit. We will have fewer errors as qubit technologies improve, but we still expect to contend with some. Error correction involves encoding information across multiple physical qubits. A system of measurements then allows the detection of errors in the qubits, yielding one reliable logical qubit. How many physical qubits will be needed for each logical qubit will vary significantly by technology type. That does it for this episode. Thanks to Yonatan Cohen for joining to discuss quantum machines. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.